Hello and welcome to my lecture for Philosophy 4400 on entropy. The purpose of this lecture will be to explain the concept of entropy and why it is always increasing. Now this is a little bit of background. So in our experience, we notice that there's a kind of asymmetry between the past and the future. We notice that people get older in the future. They never age in reverse. If you put some milk in your coffee, you notice that the milk disperses throughout the coffee. And you never see the reverse process. You never see a cup of coffee with milk mixed in with it and then see the milk coalesce together in the middle and separate out from the coffee. You notice heat flowing from a warmer to a colder place, and you don't notice the reverse. You never notice the warmer thing getting hotter and the colder one getting colder. You notice rivers flowing downhill and ultimately into the ocean. You never see the reverse. You don't see rivers flowing out of the ocean going back up into the mountains. However, this is interesting because most of the fundamental laws of physics are time reversal invariant. What this means is that the past and future directions of time play the same roles in the equations. There's nothing in the equations that shows you an asymmetry between positive and negative time. And so therefore, any sequence of events that can occur in a particular order could also occur in reverse. That is, if a particular sequence of events doesn't violate the laws, then the reversed sequence of events would not violate the laws either. There's one interesting exception to this, which is the entropy law, which we're going to discuss below, i.e. basically the fact that entropy increases in the future direction and not in the backward direction. So a very interesting question is how to explain the time asymmetry in our ordinary experience, despite the fact that the laws of physics seem to be time symmetric. Is there some explanation for the time asymmetry in terms of the laws of physics? Now, before we get to that, we have to do some explanation of this branch of physics known as thermodynamics. So in thermodynamics, there's an important distinction between the microstate and the macrostate of a physical system. So the microstate would be a state that includes the position, momentum, and other properties of every individual particle in your physical system, every molecule or maybe every atom. The macrostate would just be a state that specifies macroscopic properties, like the volume of gas that you have present in a container and the temperature and the pressure that it's under. Now, notice that these properties are all observable at a normal human scale. You don't need microscopes or anything. You can measure these things with thermometers or things like that. At the macroscopic level, we notice certain generalizations known as laws of thermodynamics. The first important one of these is the first law of thermodynamics, which is basically the conservation of energy. So energy is neither created nor destroyed. No doubt you're familiar with that. The second, and very interesting law of thermodynamics, has a number of different formulations. So these are different formulations that you can find in physics textbooks of the second law. It said that no process is possible whose sole net result is to transfer heat from a colder to a hotter body. Now, it is in principle possible to transfer heat from a colder to a hotter body, but that can't be the sole net result. That is, you have to expend some other energy somewhere else in order to make that happen. So that is like what happens with air conditioners. Second formulation, no process is possible whose sole net effect is to transform heat from a source at uniform temperature into mechanical energy. So it is possible to get mechanical energy out of heat. This is what happens in steam engines, for example, and nuclear power plants. You can get mechanical energy out of heat, but that can't be the sole thing that's happening. And you require a temperature difference in order to do the work. The third formulation of the second law, which is the most philosophically interesting one, and that's the one that we're going to focus on for the rest of this, says that the entropy of an isolated system never decreases. So if you have a physical system and the entropy of it is decreasing, that means that it must be interacting with some other object or some other physical system, and the entropy of that other thing must be increasing by at least as much. Another way of describing this is they say that systems that are not in thermal equilibrium will move toward thermal equilibrium and will remain in thermal equilibrium thereafter, where thermal equilibrium is the maximum possible entropy state for a physical system. Okay, now I haven't explained what this entropy is, but we will get to that. Now, the above three formulations are considered equivalent formulations. They're considered to be essentially saying the same thing, that is, given general well-known facts about the world, meaning that if you could violate one form of this law, like if you could come up with a process whose sole net result would be to transfer heat from a colder to a hotter body, then you could use that to figure out how to violate the other forms of the law. And so it's in that sense that these are considered equivalent. Okay, now what is entropy? Now, the original concept of entropy, originally people did not know what entropy really is. So the original concept derived from a kind of empirical generalization. So it was observed that you could define this quantity, S, such that the change in S is equal to delta Q over T, where delta Q is the amount of heat input into a system, and T is the temperature that the system is at. So it was noticed that in physical changes that we observe, this quantity is either zero or positive. So that is, you can add heat into a system at a particular temperature. The delta Q over, if you add up the delta Q over T for different stages of the process or different parts of a process, you're going to get a zero or positive answer. It'll be zero for a reversible change, and it'll be positive for an irreversible change. Here, a reversible change is a change that could occur in reverse. That is, the ending point could go backwards towards the beginning point. Now, in reality, there aren't really any events that are completely reversible, but there are things that are approximately reversible. So this is an illustration of what we have in mind there. And David Albert discusses a couple of examples like this, but let's say you have this container of gas and the left half of it is hotter than the right. So you could imagine that maybe there was a partition between the two halves and then somebody just heated up the left half, and then you can remove the partition and see what happens. Now we all know the answer. We know what will happen. What will happen is heat will transfer from the hotter part to the colder part. So the two temperatures will wind up equalizing. And so what that means is the right half is going to absorb a certain amount of heat, call it delta Q, while at the same time the left half of the box will lose a certain amount of heat, call it delta Q, right? The left half will have to lose the same amount that the right half gains because of the conservation of energy. Okay, so based on the definition of entropy on the previous slide, what is the entropy change during this process? So the right half is going to absorb delta Q. So its entropy change is delta Q over TR, where TR is the temperature of the right half. Okay, now the temperature is changing during this process, but imagine that you just take a small slice of the process so that as an approximation, you can treat the temperature as being constant, right? So then the right half has an entropy increase of delta Q over TR. The left half will have an entropy change of negative delta Q over TL. So the left half is losing heat, so that's why it's negative delta Q, and TL is the temperature of the left half at this stage of the process. Okay, now notice that TR is less than TL because the right half is initially colder. So delta Q over TR is greater than delta Q over TL. And so what that means is that the right half is going to gain more entropy than the left half loses. And so what you see is the entropy of the system as a whole is increasing, which is what the second law dictates, because this is an irreversible process. Initially, back in the 19th century, people didn't at first understand why all these things were the case. Now, a theory was developed known as statistical mechanics, which explains all of these phenomena that we observe. And this theory holds that ordinary material objects are made up of very large numbers of tiny particles, molecules, which are in rapid motion, random motion, and macroscopic properties can be identified with characteristics of these molecules. So the pressure of a fluid is the force of the collisions of the molecules with the container. The molecules are moving around and hitting against the sides of the container, and the amount of force per unit area on the sides of the container is the pressure. The temperature is the mean molecular kinetic energy. That is, on average, each of these particles has a certain amount of kinetic energy from moving around, and the temperature is just the average of that. How do we know all this? This is a good theory because this explains a number of observations that we make at the macroscopic level. So, for example, if you expand a gas by sliding out a barrier perpendicular to the direction of the expansion, that does not affect the temperature. Right? So imagine that you have a box that's got some gas in the left half and the right half is empty, and there's a partition in the middle, and you pull the partition out, right? Then that doesn't affect the temperature. On the other hand, if you expand the gas by moving a wall out parallel to the direction of the expansion, so like if you had a piston and you pull it out, then that will affect the temperature. That will decrease the temperature. And this can be explained by this kinetic theory of gases, because as the molecules of gas collide with the piston, if the piston is moving out, so it's moving away from them, so when they collide and they bounce off, they're going to bounce off and wind up going slower than if they hit something that was stationary. Also, if you compress a gas, so if you had the piston and you push it back in, that will increase the temperature, and that's explained by the fact that if you have these molecules of gas hitting this piston that's moving towards them, that will increase their kinetic energy. And that's just explained in terms of Newtonian physics. Also, if you heat up a gas, that will increase its pressure, also explained by this theory, because if you heat up the gas, that means that the molecules will have more kinetic energy. That is, it means that you have faster moving molecules, and that means that when they collide with the walls of the container, they will collide with greater force, so the pressure will go up. Okay, so there's various things like this that can be explained by this theory. Another interesting piece of evidence is the phenomenon known as Brownian motion. This is a phenomenon where if you observe tiny dust particles, they kind of jerk about randomly. And this is explained by the hypothesis that there are these molecules inside them that are just kind of constantly vibrating randomly. And that can lead to observable movements in a very light dust particle. Okay, now I'm going to turn to trying to explain what the modern understanding of entropy is. And to explain this, we first have to introduce this concept of phase space. So the phase space it's similar to the configuration space that we talked about in a previous lecture, except that this is a 6n dimensional space where n is the number of particles in a physical system. So if you have one particle, then you have a 6-dimensional phase space. If you have 2 particles, you have a 12-dimensional phase space, and so on. And why 6? Well, there's 1 dimension each for the position of each particle and the momentum of each particle in each of the 3 directions in physical space. So a physical system will occupy a point in the phase space. As the microstate of a physical system determines a specific location in the phase space. The system will then move deterministically through the phase space over time. In classical mechanics, so neglecting the possible randomness in quantum mechanics. Note that possible phase space trajectories cannot cross, given determinism. That is, given determinism, from a particular point in phase space, there's only one possible future. And so therefore there cannot be a branching. Okay, and now a key mathematical observation is that what we think of maybe intuitively as disordered arrangements correspond to larger regions of the phase space than more orderly arrangements. So for example, if you have all the molecules up in one corner of a room, that would be a very orderly arrangement, as opposed to a case where the molecules are just distributed throughout the room randomly. And the situation where the molecules are all in one corner of the room, so that macro state corresponds to a very small region of the phase space. There are many more ways of distributing things so that the molecules at the macroscopic level look like they're spread throughout the room than there are ways of distributing the individual molecules so that they look like they're all in the corner of the room. Okay, this is analogous to the fact that if you flip a coin a large number of times, there are many more ways of having outcomes where about half of them are heads and half tails than there are ways of having all of them be heads, or almost all of them be heads. Okay, as another example, if you have some cream in a cup of coffee, there are more ways of having the cream basically spread throughout the cup than there are of having the cream all in one small part of the coffee cup. And this is going to have something to do with why we see entropy increasing over time. Okay, so now here's a modern theory about entropy. This was discovered by Ludwig Boltzmann. Maybe the entropy of a physical system has to do with the size of the region of phase space that corresponds to that macro state. And so Boltzmann discovered this equation, S, the entropy, equals K log N, where K is a constant and N is the number of possible microstates that are compatible with a given macro state. For the case where you have an infinite number of possible microstates, you take the size of the region of phase space. Okay, you might wonder why you're taking the log of n instead of just taking n. Basically, the reason is to make entropy additive. So if you have a physical system that can be split into two parts, you want the entropy of one part plus the entropy of the other part to be equal to the entropy of the whole. And so you have to take the log of the number of microstates, because if you don't, then the entropy will be multiplicative. Right? When you have two subsystems and you combine them into a larger one, the number of possible states multiplies. But you want the entropy to add. But the log of the number of microstates adds. Okay, so high entropy states are more probable given just a random selection of a position in phase space, simply because they correspond to larger regions of the phase space. Or in other words, there's just more ways of making a high entropy state obtain than there are ways of making low entropy state obtain. Another way to describe this is to say that a low entropy state is more informative. That is, if you know the macro state and it's a low entropy state, then you have more information about the micro state. You can narrow down the micro state more. Okay, so now, given this understanding of what entropy is really about, we can explain why entropy increases over time. So here's one way to think about it. Imagine that you have this box with a gas that is non-uniformly distributed. Gas of type A is on the left, and gas of type B is on the right. For example, it could be there's oxygen on the left and nitrogen on the right, or it could be there's hot gas on the left and cold gas on the right. The argument works either way. Assume that the molecules in this gas are all just moving around randomly. So periodically, one of the molecules will cross from one side of the box to the other, just from random motion. Now, a molecule crossing from the left to the right is more likely to be a type A molecule because, by stipulation, gases of type A are on the left. And a molecule that crosses from the right to the left is more likely to be a type B molecule. At the start of this, they're all type B on the right, so it's 100% likely. As they mix more and more, the proportions are going to get more equal. Okay, but it will always be true that it's more likely that the that the molecule going from the right to the left is of type B until the proportions are equal. Okay, so if you repeat this reasoning for trillions of molecules, then you get an extremely high probability that the gases are going to mix approximately equally over time. This is just going to continue until at the macroscopic level, it's about equal amounts of gas of type A on the left as on the right. Okay, here's a second argument due to the American physicist Josiah Willard Gibbs. Assume that there's a system that's in a confined region of physical space, like the way the Earth is in a confined region of space, and there's a fixed total energy E. So in accordance with the first law of thermodynamics, the total energy of this system doesn't go up or down. It can only transform its form. So this system is going to move around the phase space. Remember again, the system has a location that's a specific point in this very high dimensional phase space. So it's going to move around its energy E hypersurface in the phase space. What is this? The energy E hypersurface is a subset of the phase space that has energy level E, because other regions of the phase space will require the system to have more energy or lower energy, because they will involve the particles moving faster or slower than they actually are. Right, so there's only a particular region of the phase space that has that amount of energy, the actual energy of the system. So the system, because it has to continue to have that energy level, it can only move around this particular portion of the phase space. Now suppose that it moves randomly around the energy E hypersurface. It's said that its trajectory is ergodic, which means roughly that the amount of time that it spends in a given region of phase space is proportional to the size of that region. Note that just as a mathematical fact, it turns out that almost all possible trajectories that you can come up with are ergodic. Okay, so also it turns out that almost all of the energy E hypersurface corresponds to thermal equilibrium. That is, it'll be almost all of it corresponds to a state where at the macroscopic level it looks like everything is about uniformly distributed. And so therefore, we should expect that the system will spend almost all of its time in thermal equilibrium. If it's just moving around randomly, if at a given point in time it's not in thermal equilibrium, it's heading towards that, just because almost all of the space is thermal equilibrium. When it gets into thermal equilibrium, it will spend a long time there because there's not that much else to go to. There's not much other space for it to go to. Now, in observed fact, material objects actually behave in the way predicted by this theory. They behave just as if they are in a randomly chosen region of the phase space compatible with their observed macroscopic condition. So, for example, you can use this theory to explain the rate of diffusion of gases, right? If you introduce some gas in a container that's different from the gas that's already in the container, then you can observe the rate at which it spreads throughout the container, and you can get a correct prediction based upon this theory. Okay, these are a couple of confusions that David Albert discusses in his chapter. So some people commit this mistake. They think entropy isn't a property of an individual physical state because the entropy has to do with the volume of phase space that the system's state takes up. But a physical system at a given time is always in one specific microstate, which occupies exactly one point in the phase space. So, if the entropy was a property of the particular physical system, it should always be the same. In fact, it should always be zero because the volume of that state is zero. Okay, so the response to this, and I'm just reviewing this to make sure that we understand conceptually how entropy is understood, right? The correct understanding is, so entropy is not defined in terms of the phase space volume of the microstate. The microstate always has a phase space volume of zero because it's a specific point. Entropy is understood in terms of the volume in phase space that the current macro state takes up. So the macroscopic state, where you have material at a certain temperature and pressure, is compatible with a range of different microstates. That is, there's a number of different ways of arranging these specific particles in a physical system that would make it macroscopically indistinguishable, like having the same temperature, having the same pressure, and so on. Okay, and different macroscopic states have different volumes of the phase space that are indistinguishable, right? Indistinguishable at the macro level. Okay, here's a second confusion. Individual real systems don't have to evolve towards equilibrium. They don't have to, they're just more likely to. Therefore, the second law of thermodynamics must really be a claim about probability distributions over infinite collections of possible systems. This derives partly from the way that the second law is traditionally formulated if you look at physics books. So they will traditionally say things like entropy of an isolated system always increases. And so this can lead to this confusion where you think, well, how can this law be correct that it always increases if we just gave this probabilistic explanation for why the entropy of a particular system must increase? So the law must be about something other than the particular physical system. The correct understanding is, well, the traditional formulations of the entropy law are not exactly true. That is, it's not exactly true that entropy always increases. That's false. What's true is entropy almost always increases, or more precisely, it's overwhelmingly likely that you'll observe entropy increasing if you start from a state that is not in thermal equilibrium. It's overwhelmingly likely, but it's not 100% likely. It's just that it's so likely that we don't expect to ever observe an exception. In the history of the human species, probably no one will ever observe entropy decreasing at the macroscopic level, but there is a non-zero chance of that. Here's a third possible confusion. Equilibrium is a state that doesn't change over time, right? Isn't that just the definition of equilibrium? But there's no actual physical state that's like this. So maybe equilibrium is a property of something else other than the actual physical state of a physical system. Like maybe it's a property of a probability distribution or something like that. Right, and as David Albert says, this notion of thermal equilibrium is a slight misnomer. Systems that are said to be in thermal equilibrium, they don't stay that way forever. It's merely that they stay that way for an extremely long time. So if you get a system in thermal equilibrium, you should not expect any human being to ever observe it leave thermal equilibrium, unless, of course, a person introduces energy from outside the system or something like that. Okay, now that's all I have about entropy for now, except I want you to think about this question, which is kind of what we started with. How do we get a temporal asymmetry? Because you might think, given the arguments for increasing entropy that we discussed in the previous slides, you might wonder why we can't give similar arguments for entropy increasing into the past. So if you're not in thermal equilibrium, you expect that in the future direction, the system will probably be closer to thermal equilibrium. But also, why can't you similarly argue that you should expect that in the past the system was probably in thermal equilibrium? Again, by saying, well, almost all of the phase space is thermal equilibrium. So in the past it was probably in thermal equilibrium. So entropy probably increases into the past as well as into the future. Right, so we will discuss that more in the next lecture.